Hello, hello. Welcome to section 2.1, Networks and Synchrony, where we talk about how messages propagate over our network and different models we can use to analyze this propagation. So, just as before, our nodes are sending messages to each other, but let's look at how these messages arrive. So here we have two gerbils, Alice and Bob, and Alice wants to send a message to Bob, and that message takes some time to go over the network. Bob receives the message, but then Bob has to open the message, read the message, and see what it means. And so the actual time that this took for Bob to understand the information was the time to propagate the message plus the time to process that message. And so if we say, maybe the network latency plus the processing time, this full thing, takes 5 seconds. So 4 seconds for network latency and 1 second to read the message, for instance. So now if latency is equal to infinite seconds, well, we can just wait. Oh, that's really just a dropped packet. And so we can do this kind of timeline where we show Alice sending a message, hello world, and Bob receiving it saying, my name isn't world, it's Bob. And so Alice sends the message, Bob reads the message, and at this point, now that Bob has read the message, returns with my name isn't world, it's Bob, and Alice reads the message. So this is a way that we can kind of model our network messages going through, and it took a grand total of 10 seconds. Now, great, but this is exactly 5 seconds, and this is exactly 5 seconds. But really, we don't know how long messages normally take. This is kind of like God mode that we're playing here. And so what we'll do is we'll actually come up with different models for our message propagation. One called synchronous, where we say there is an upper bound. We don't know exactly how many seconds a message takes to propagate, but we know it takes less than 5 seconds, for instance, or less than 10 seconds. Now, there's another model where we call it partially synchronous. This is where there is an upper bound, as in our messages will eventually arrive, but we just don't know how long it will take for them to arrive. So it might take a minute, it might take an hour, it might take a year. And then finally, there's asynchronous networks, which we don't know if the message will ever arrive. It could be infinite time for the message to arrive, which basically means it's a dropped packet. So let's first look at synchronous networks. How would we think about this? Well, now, in a synchronous model, we are going to say that the message arrives sometime below 5 seconds. So this is 5 seconds, and now our message arrived right here and was processed right here. And so that, let's say, took 3 seconds. But it might be 4, it might be 1 second, it might be any number of seconds up to 5 seconds. And so as long as we've waited 5 seconds, we have a guarantee that it's been received and read. Now, messages are received by all interested parties, right? This is an important note. So if Alice is not just sending to Bob, Alice is sending to a whole network, then it must be the case that all parties received that message within the time 5 seconds or whatever our synchrony bound is. So now all messages have been received by all parties. Now, that is synchronous networks. Those are the strongest assumptions, right? That's a pretty strong assumption. Now, partially synchronous network is when we don't know the bound. So right now the bound is 5 seconds, but we don't actually know. And don't fear, it's okay, not a big deal. We can actually just put a constant. We can say, okay, here, delta is going to be our upper bound on network propagation. It might be 5 seconds, it might be 99999. We don't know, but we can at least reason about it. So we can call delta to delta, and we can say, okay, at least by delta, we don't know what delta is, all messages will have been received, and to delta, Bob will have sent the message back. So that's pretty realistic in some ways, right? It's basically like Alice is trying to propagate. Maybe it gets dropped a whole bunch of times, but eventually Alice gets the message through. So this is the guarantee that messages eventually will go through. And this is really nice for proving things like liveness. If all the messages will eventually go through, then it follows to reason that our protocol will continue moving, right? If our messages stop going through, then of course it makes sense that they would halt. So that's partially synchronous, but now let's look at asynchronous networks. So in asynchronous, it could be infinite time for messages to go through. It could be the heat death of the universe. And so that's kind of like Alice sending a message, the shark eating it, and then the shark eating Alice. Oh, sorry, Alice. But that's the most realistic, right? Our messages may be dropped entirely and never sent again. So in reality, the messages may never arrive, but it can be useful to use these different models because within different models we can prove different properties of our protocol. We can say our protocol is live in a partially synchronous setting, but we don't guarantee liveness in an asynchronous setting. And all of these, models get less and less, fewer and fewer assumptions as they go on, right? Synchronous, many things work. Partially synchronous, some stuff breaks. And asynchronous, a lot of stuff starts breaking. So next up, we've got the double spend problem, section 2.2. Let's dive in.